Hey, recording's rolling. It's Monday, October 6th, but you guys just turned in your dynamics quizzes. We're moving on to Centripetal Force Lab. So today, actually, this lab's going to take us a couple of days. I'll show you some setup and how to go through this. You guys have a slide page. Okay. So that'll take a little bit of setup. But the rest of this week, now, this week's a little bit weird for a couple of reasons. One is that there's a PSAT coming up on Thursday. So there will be testing in my room. So my first 4 classes are relocated. Right, this is my relocation schedule. Right, so you guys know where you're relocated for first 4 classes. This is posted to Google Classroom. Actually, all the relocations for all the classes I posted. Also, all the testing locations. So there's an Excel file also in Google Classroom. I posted it almost a week ago. It shows for every single student is testing. So if you have a question, if you think you might be testing, check that out. Right, so is there any question about PSAT? Okay. Now, guys, if you are not testing, which is a lot of you guys, and you're being relocated, then what I'm going to recommend is that you hop on AP Classroom, just open your laptop and try to solve it. Because AP actually organizes this a little bit weird. As of a couple of years ago, they took all this dynamics that we've been doing for the last 3 weeks, and also all this circular type motion, which we're going to do for about the next 3 weeks. They pushed it all into one giant unit they call Unit 2. So probably right now, you can probably answer most of the questions on AP Classroom. And then by Thursday, definitely so. Maybe even a couple of these circular motion questions, possibly by Thursday. We'll see, right? Friday is the end of quarter 1. So for all your classes, including this class, make sure that all your assignments are in by this Friday. Because, guys, by the time that Tuesday rolls around, if you turn something late on Tuesday, there's nothing that your teachers can do about it. Like, I could try to put the grade in the grade book, but it doesn't actually go in. And, finally, note down here, you guys probably know a YouTube channel called Vsauce, maybe? Some of you guys? Right. So I will post a link to a really good video it has called Spinning. Here, I'll play you guys just a little bit of it right here. Just a little bit. Right, so, right. It shows how things work in a rotating sense. Now, there's a lot of parts to this video. Some parts that we won't even get to in this class until probably like December, January. You guys watch this car go around a curve. Right, so there's the car going in a straight line. You guys see that green velocity vector? Well, that would be a velocity vector, wouldn't it? That green, right? Right, so it's just going in a straight line, go straight. Right. And now, for the first time in this class, we're saying, hey, what happens if you make a left-hand turn? Now, you can feel that inside the car, right? You can feel that? Now, anything you can feel has something to do with like forces and accelerations. But here, this is it's maybe what we're going to call a centripetal force or a centripetal acceleration to have something going around a curve. Now, what's the value of that force you feel? Here, don't you feel like thrown to the side? Here, guys, if you're making a left-hand turn, which way do you feel like you're thrown relative to the car? Yeah, it feels like you're thrown to the right? But here's the funny thing. Guys, watch this animation. Aren't we, from the point of view of this animation, we're up in a helicopter looking straight down? You guys see that? We're up in a helicopter looking straight down. And suppose there's a blue marble. It's just sitting right in the middle of the car floor. Blue marble. You guys see that blue marble? Right? Now, when this guy makes a left-hand turn, says, okay, it looks like the marble's kind of drifting to the right of the car. Right? But from our point of view in the helicopter, is that blue marble making anything going to the right? No, it's trying to go in a straight line. Isn't that Newton's first law of motion? Things only ever want to move in straight lines. The car's moving to the left. That's why if you're inside the car, you think it's being pushed to the right. But it's not really. It's just trying to move in a straight line. Now, so from your point of view inside the car, you would call that a centrifugal force. So like some kind of center fling force. It looks like it's pushing it away from the radius of curve, from the center of the circle. But that doesn't actually exist from our helicopter point of view. Us inside the helicopter, we're in what's called an inertial frame of reference. We're the non-accelerating observer inside the helicopter. We're just looking straight down. We're saying, actually what happens is that when this blue marble hits the wall of the car, the wall of the car provides what's a normal force, which acts as what's called a centripetal force, a center-seeking force. You guys see you can fit a circle flush right here, a circle flush to that curve, right? And guys, where's the center of the circle? Is it like kind of up here, like near the top of the screen? Right? And aren't the actual forces pushing everything like upwards towards the center of that circle? Yeah. No, there's different kind of forces that can act as a centripetal force. I'm never going to label, guys, I'm never going to label one of my forces on my free body diagram as centripetal force. I'm never going to do that. It's always one of your classic forces. In this case, it would be the normal force from the wall, pushing the marble, the blue marble. Right? Guys, what about the car itself? Guys, if this is a flat track, if that road is flat, what force is actually allowing the car to make the turn? Friction. Yeah, friction. So that could be acting as the centripetal force, right? Or what about this? What if the road is banked? Could the road being banked help the car make the turn even without friction? Yeah, so that'd be some component of the normal force. Or what you guys are doing, Again, this is part of a larger video. I will post that link later today. Oh, yeah, here. Get that. Now, what you guys are setting up is looks like this, and this is the actual physical example here. It's gonna look like this. Okay? So I'll show you guys a demo real soon where you have this pipe set up, you have a string, you have a couple of canisters that are maybe different masses or weights, right? I'm swinging this around in a circle. Okay? And there's going to be some tension in the string that's providing the centripetal force to hold this top canister in a circle. You guys get that? Right? So, here, I'll go ahead and do this. Right, so if you're watching the video, then off screen, I'm just going to set this up and show you guys. Okay? Right, so I will get this spinning. Okay? Now, do you guys see how the radius of curvature I'm keeping constant? Like it's not getting bigger or smaller? Right, so that would be an important detail you want to. Now you can hold a meter stick. Can I hold a meter stick right next to that, and just make sure that the radius is not growing or shrinking? Okay. Guys, also notice this, guys. Am I grabbing this bottom one like this, and I go like Am I doing that, or am I just letting the weight naturally provide the force that's necessary to hold us together? It's just hanging out here by itself. You guys see that? I'm not like grabbing this thing. I'm just letting it hang down. Okay. And what that means if this bottom canister is in true static equilibrium, notice it wasn't moving up or down. Isn't that true? Right? It was just hanging out right there. True static equilibrium. Its weight would be pulling down. And guys, what force is pulling up? Tension. Is that tension here the same as this tension right here? It is. Yeah, and that tension is acting as a centripetal force, holding this top canister along a curved path, in motion on a curved path, right? Which is, again, equal to the weight of the hanging canister. So the bottom canister is in true static equilibrium. True equilibrium. It's not even moving. Right? But the top canister, guys, is the top canister in true equilibrium? No, because it's moving on a curved path. Right? Now, sometimes you'll hear the phrase dynamic equilibrium, and what they mean by that is this radius is not changing, right? So it's not drifting closer or further away. So this radius is constant, right? So dynamic equilibrium. I probably wouldn't write that on an AP exam, but you might see that. Okay. Right, but yeah, so this top one is not in true static equilibrium, but it's moving on a curved path. So, guys, what variables do you think might hold this whole system like that with a constant radius and so on? Right, what variables are we checking off here? Yeah, maybe this hanging weight. Like, guys, if I make this one really, really heavy, if this is really heavy, do you think I would have to spin this faster or slower? Probably faster makes sense, right? I mean, just sort of hypothesizing. And even if that's true, I wonder what is that relationship? Like, guys, if I triple this weight, would that be triple the speed, or more than triple the speed, or less than triple the speed? Or would it be a slower speed? Huh. All right. So, how does this weight affect this speed? Guys, what else could maybe affect how fast you have to spin it around? Yeah, how about the mass of the swinging one? Right. What if I make the mass of the swinging one really, really heavy? Would it have to spin this faster or slower? I'm hearing a denomination for each one of those, right? And then whichever one of those is correct, like what more specifically is the formula that connects those? Like how are these related proportionally? Okay? And finally, guys, do you think there's a relationship between this speed and this radius? Right? Like for a small radius, what would the tangential speed be? Like how fast? Like if you point a radar gun at this, it'll tell maybe like a speed. Okay? Or what if I held a speed gate up to it and I just get the canister swing through the speed gate? Okay? Right. So I'll call this a tangential velocity or just speed is okay. Okay, you guys see that? Right. What does that have to do with this radius? So do you guys see four variables juggling around? This R, this M, this D, and this F. You guys see those four variables? Right? So, what I'm thinking is that just like your guys' car and incline lab, if there's a bunch of variables floating around, I need to split you guys up into different experimental groups. Right? There should be a playing card taped near your desk. Right? Do you guys see a playing card with a suit on it? So I'm going to split you guys up into these experimental groups. Okay? If you have the spades, what I want you guys to do is to here before I go down the list here. Right? Everybody's going to treat the speed as sort of the dependent variable. This lab just works out really nice that way. So let's just go with that. Right? So if you have the spades, what I want you to do is change out the mass of the swinging canister. Okay, you guys get that? And how do you do that? Well, let me show you how this is actually put together. So an empty canister, do you guys see on the board behind me? It says the large canister is 12 grams. This is the large canister. So empty canister, 12 grams. Okay. And there are some small canisters back there that are 6.5 grams. Okay. Now, guys, can I pop this open? And I can pop in lab weights. So this one is marked 10 grams. So guys, if this canister is 12 grams, that includes the lid, and this is 10 grams, and I pop this all together, how many grams total? 22, right? 10 plus 12 is 22, right? Like that. All right, now watch this too. Okay, so I want to do this. Don't want to take the string and just barely put the string right there, and just like that, and then start swinging this around. No, he's gonna fly off. But watch this. Watch this. What if I cross this over like this? Oh, look at that. You see 1, 2, 3, 4 points of contact. Now that'll never come out. And if you're still not sure about that, there's a bunch of masking tape back there, so you can take some masking tape and also throw it. Okay, right, get that. Right. Okay, so that's if you have the spades. You're changing out the swing canister. If you have the diamonds, I want you to again, each one of these you're controlling everything else. So if you have the diamonds, you're changing out the hanging weight. Okay, so that's like the other canister. So similar type story. Like I said. Okay, and then you leave everything else controlled. So we would leave the other canister locked, and you would also leave this radius controlled. Okay. Okay. Speaking of controlling this radius, this is one of these labs that if you're really meticulous about this, like if you hold up your meter stick next to what you do, suppose you want to have this radius locked in at like 50 centimeters, and you make sure it's locked in at 50 centimeters, and you leave that really well controlled, your numbers will come out really nice, and the graphs will come out really nice, and this lab works perfectly. On the other hand, if you're really messy about this, like you're letting the radius just like grow and shrink and it's not controlled very well, or you're not keeping very good track of the weight, or you're like grabbing this bottom line or something, the numbers aren't going to make any sense, the graphs aren't going to make any sense, and then you just have to take my word for what the official physics is. But if you're really careful about slash, the graphs look really, really nice and lead straight to the technical equation. Okay? And finally, if you have the clubs, I want you to leave the two canisters locked, so you're not changing this mass or this weight. Okay? But what you are doing is you're treating this radius as an independent variable. So maybe you started at 30 centimeters, and then you go 50, and then you go 70, and then you go 90. And all of those could be independent trials. Right, you guys get that? Okay. If you have the hearts, let's treat, I think just you guys have the hearts. Let's call it a wild card. So you guys get to pick which lab you want to do. And I have 2 here, 2 here, and 2 here. And you guys can do whatever you want. Right, so we'll have plenty of trials. So if we get a missed trial, then we can call another group. Yeah. Right, you guys good so far? What's going on? Okay. Now, let's go across this table I gave you. So I gave you a table with some spaces for some graphs later on. It's going to take us more than one day. Okay. And so the table in front, you can gather your data. Now, my earlier class, they weren't able to gather a whole lot of data. So I'll have to give you guys at least some time tomorrow to also gather some data. But how do you read this table? Right, so first column says the mass hanging. Now, I went ahead and said grams. It's kind of a practical unit to work in. Because in this class, you don't normally work in grams. You normally work in what? Kilograms. And how do you go from mass to weight? You very simply can multiply by what? 10. Yeah, 10 works, 9.8 works, and that'd be meters per second squared. But if you have kilograms, multiply by 9.8 to get newtons. Right. Well, what if you only have grams and multiply by 9.8? That gives you not newtons, but what? Millinewtons. Because it's off by a factor of 1 over 1,000. You guys get that? Right? So suppose this was like 22 grams. And if I do 22 grams times 9.8, I'm getting like 216 about millinewtons. Yeah, I can do that. Okay. Next column, the swinging mass. Okay. Now, if you've been paying attention to what I've been showing you guys, I really care about the weight of the one that's hanging, and I care about the mass of the one that's swinging. You guys got that? Okay. So if you see mass out of context, like this next column, see it says 1 over mass. Which mass would this be referring to? The swinging one or the hanging one? The swinging one. It's always the swinging one. Okay, so it's swinging one, I care about the mass. Okay, the swinging one, I care about the mass. The hanging one, I care about the weight. Okay, all right. So this table, some of these you can record or measure. Some of these you can calculate as we go on. Okay? So radius. I can measure the radius. A practical unit might be centimeters, 2 centimeters, right? So we got grams today and centimeters. That's okay because at the end of the day, by the time you get to the graphs, all I care about is proportional relationships. So as long as you have all consistent units, it all works out. Take 1 over radius. That'll make sense later on in the lab. Okay. Now, working up for the speed. These last few columns all have something to do with the speed one way or another. Okay? Like I'd really like to know what is this speed or what I might call tangential velocity. Now, maybe I could hold up a speed gate and it could whiz through. That'd be kind of hard to grab, though, right? Can you guys think of a practical way you could calculate the speed? Aha! Yeah. Something about counting revolutions and how much time does that take? right? Right? Guys, what's the definition of speed? Speed is what divided by what? Distance over time. Yeah. Like how far does it go and how much time? You just divide it, distance over time. Right? Oh, what is the distance around a circle called?
The radius.
The circumference. And how do you get circumference based on radius? Circumference equals
Which one's the easiest lab?
the easiest lab?
Yeah, which one?
Out of these, they're all about the same, I think. Yeah. So I think isn't circumference equal to 2 pi r? And if you knew how much time it was by time it with the stopwatch, could you do this? The speed would be 2 pi r divided by t. You guys see where that comes from? Right, circumference divided by capital T is time period today. Okay. Right. But here, one more recommendation. Isn't starting, stopping, and stopwatch? Isn't there a lot of error usually associated with that?
Yeah.
So what I'm going to recommend you do is to count up 10 revolutions. So you do this: get swinging, find a start stop point, and then go like this: 0, 1, 2, 3, 4. And then when it gets up to 10, then stop it. You guys know you're going to start at 0, right? Right? Because when you start counting, it hasn't gone around yet. Okay. So count up to 10, and then stop the stopwatch. And if you're off by like 1 second, and then you divide by 10, now your error also gets divided by 10. You guys get that? Tricky correct. Okay, so, and then last column, go ahead and square that speed. So if you get like 20 meters per second, square that and get 400, and that'll make sense by the time you get to graphs. Okay? All right. Any questions so far? Okay. All right. So one more thing for you guys. One more thing is, all right, so this is one of these big labs. I'm going to be referring to this lab probably up until the day before the AP exam. Okay. I'm going to help you guys get an AP style write-up started. AP style write-up. So AP style write-up looks like this. Okay. So you guys on the separate page of paper. Here, get you guys started here. All right, let's go. Make sure your name is on all these materials. Your name is on your. Did everybody already write their name on their table? Great. So when you eventually turn this in, I did give the points to you on your write-up. So question. Okay. Now the master question here is, what's the relationship? Yeah, I'm helping you guys start on the AP style write-up. Okay. The master question here is, what's the relationship among these 4 variables? This weight, or you could say the tension of the string, is the same number. Okay. This swinging mass, this radial size, and this corresponding speed or tangential velocity. Okay. But depending on which card suit you have, you can focus that question. You can narrow it down to one of these 3 questions. Okay. So what is the relationship between something and something? You know, you guys don't draw blanks. Right? So, for example, if you have the spades, you could say between the V and the M swing, right? If you have spades, right? For a mass swinging in a circle, right? Or something like that. Right? There might be different ways to word that, but some version of that. Right? So AP usually gives you the question, right? And then they say, well, how can you design an experiment to test this relationship, or to, right? So next part, they'll always ask you for measuring equipment. Measuring equipment. Now, regardless of which of the 3 experiments you're going to do, everybody actually has the same 3 pieces of measuring equipment. Guys, what's one of them? You're measuring with a what? Meter stick. Meter stick. Because you need to measure the radius. Everybody's measuring the radius, either to control it or to, even if it's as an independent variable, right? You're going 30, 50, 70, 90 centimeters, right? Or you can control it like all the, if it's controlled, guys, if it's controlled, again, that could be either the spades or the diamonds. You're controlling the radius. Then lock it into some number all class periods. So if you pick 50 centimeters for your radius, then that's it. Every single trial is 50 centimeters. Okay. I heard somebody say stopwatch. Right. And with the meter stick and the stopwatch combined, you're able to eventually calculate the speed, right? And I showed you how to do that. Circumference divided by time interval. Okay. And also, guys, how do you? What else do you think you need to measure?
Scale.
Yeah, you could say a scale, or back there I have a triple beam balance. triple beam balance. Okay. So pick your favorite and write one of those. Okay. So if you get access to that, you can definitely be using that. Okay. If it's too crowded back there and you can't quite get access to the triple beam balance, then you can play off these numbers off the board. The small canister is 6.5 grams, the large canister is 12 grams, and then you can add whatever lab weights to each of those. Okay. Right, so that's measured equipment. All right, 3. Procedure. I'll get you guys started with this. Now, analysis is going to be all these graphs. So analysis is taken care of by the graphs. And conclusion, we're going to come up with some equation, like some master equation. We'll take the 3 perspectives, the 3 different experiments, and push them all together into one giant expression. Okay. So, and I'll help you guys start. Okay. Briefly describe the setup. So, procedure. So, AP says you want to do this experiment. So, someone else in triple force. Maybe they ask you this question. And then, a little question mark. Okay. They say, how would you set this up? And you say, well, first I would do the setup. I would put a string through a pipe, attach safety canisters to each end of the string, and then whirl the top canister in a circle, keeping the radius a measured value. You good. With bottom canister in equilibrium. Okay. All right. There's different ways to write that. Earlier today, I wrote it slightly different this way. Here, right. But that's basically all I'm looking for. Something where you can describe this picture. Right? If you can describe this picture, that's all. Oh, yeah, that.
Redraw the graphs on the paper.
No, I gave you guys the access to the graphs. Okay. So if you have the so what do we do with the graphs? Okay. So you first get as much data as you can today and probably a little bit into tomorrow based on this paced out earlier. Okay. If you have the well, here, maybe I'll do this in order, but I got on the paper. Okay. So V versus F has something to do with the diamonds. V versus M has something to do with the spades. And then on the back page, V versus R has something to do with the clubs. Something like that. Okay. Yeah, so we'll take these 3 perspectives of the story and we'll push it into one master equation that will be the answer to the lab. Okay? All right. Yeah, I'll do that to you too. Right. But here, I'm going to close down this recording and yeah, I will walk around, help you guys out to gather lots of data.